today I would introduce the basic terms and terminologies which would be used throughout the course. So these are actually prerequisite for this course. Although the students have already done some course on these, that is the prerequisite. However, I would like to present those definitions because sometimes some terms and definitions differ from book to book. So to have the consistent notations and definitions, so let me very quickly give you the basic theory of measures and integrations, and what do we mean by probability measure, and the notion of convergences, what do we mean by integration with respect to a measure, and notion of convergence of integrals. So these are the things which we are going to see today very quickly. Okay, so we start with the question, what is a sigma algebra? So why do we call about sigma algebra? See, for example, when we look into the application in probability, so there we talk about events. What are events? Events could be a very elementary event, like one particular occurrence of some sample point, or event could be a collection of sample points. Okay, for example, when one tosses a coin for 5 times, then one can say, okay, my event is occurrence of head in first 2 trials, etc. So event could be elementary or composite in manner. So in principle, event is collection of sample points. Now one should also consider space of all possible events. Since events are itself a collection, that means a set, so space of all possible events is a collection of collections. So these collections should have certain particular structure. What are these? For example, if I can answer to the question, what is the probability of non-occurrence of an event A, if I know the probability of occurrence of event A. Okay, our basic intuition says that if I know the probability of occurrence of event A, then probability of non-occurrence of the event A should also be known. That would be just nothing but 1 minus of the probability of A. Therefore, if I say A is an event, so the complement of A, that is A complement, should also be an event, okay, because we can actually talk about its probability. Now if I say that, okay, A, B, C, D, etc., these are all say for example, I start writing here. So if A is in my event space, okay, that would imply that a complement should also be in that event space. Okay, and again, if I have A1, A2, etc., these countably many events, all are in event space, and then I ask that occurrence of any of these, is it an event? So is a new event that A is occurrence of either of these. Okay, so that you can write down in mathematical notation union of AI, union over all possible I. So if we say that omega belongs to A, I mean that if and only if omega belongs to AI for some I. Okay, so we know that this is the rule of union. So what is the bottom line? The bottom line is that if A is in the space of all possible events, the A complement should also be in the space of all possible events. And if I have a countable collection of events, then their union should also be in the collection of events. Okay, so based on this, so let us define what we call as space of events. Okay, and that we should have this structure, and there is a name for this structure. We call this sigma algebra. So what is sigma algebra? So let us write down what is sigma algebra. So first thing is that it is a non-empty collection of sets. So sigma algebra on some set omega which is non-empty, okay, that is the collection of subsets. So sigma algebra, I denote, say E is a sigma algebra, okay, E is a sigma algebra on omega which is non-empty. What does it mean? It means that E is a subset of power set of omega. Often we write down power set as 2 to the power omega also, correct? Set of all subsets of omega, and we need it to be non-empty. So it is non-empty. I write down it separately. So if I just say empty set belongs to this collection, this is done. Okay, this is non-empty because the empty set is here in this collection, and we require that if A is in this collection script A, then we must have a complement is also in script A, okay. And if I have a collection of events, okay, an which is in E, okay, every an is in E, okay, for all n is equal to 1 to infinity, then I must also get that union of n is equal to 1 to infinity is also in script E, okay. So that is the definition of sigma algebra, okay. And I have explained why do we need this structure, because if you do not have this structure, then you would not be able to answer to the question that if I know probability of a set A, what is the probability of a complement? I cannot ask that question if that set A complement is not an event at all. Okay, so this is the structure that we call sigma algebra. Next, we define what do we mean by a measure, okay. So we go to the next slide. So here we have omega and then E. So E is a sigma algebra. So if omega is a non-empty set, E is a sigma algebra on omega, then you call omega E is a measurable space. Measurable space, and then mu, which is defined on the script E, that means defined on a sigma algebra and taking value 0 to infinity closed. What does it mean? That all positive real number including the plus infinity. So that is called a measure if the followings are true. First thing is that mu of empty set is 0. Second thing is that if I have countably many disjoint events, so if an are if a sequence in the sigma algebra E where ans are disjoint, then mu of union of an n greater or equals to 1 is equal to sum of mu of an, okay, n is equal to 1 to infinity. So what does it mean? The right hand side can be given a proper meaning. Why is it so? Because although this is an infinite sum, but these elements are all non-negative. Why is it so? Because look, the mu is taking value 0 to plus infinity, okay. So this is sum of non-negative terms. So if you look at the partial sum sequence, that is always increasing. need not be always bounded, but is always increasing. So if it is bounded, it converges, the value would be this meaning of this sum. If it is not bounded, that means it is unbounded, then this sum would be plus infinity. So these are when a map satisfies these conditions, then we call that as a measure. Okay, so it gives a measure of a set. Okay, so this second property is called the additivity property. Okay, additivity property of the measure. What is probability measure? So omega. So in my successive lectures, I would use script f mostly to denote the sigma algebra. What I was talking about script e till now, okay, I would switch to this notation script f. Script e sounds like space of events, but however f stands for field. So in the literature or textbooks of probability theory, you would see that okay, sigma algebras are often called as sigma fields. So that is also one reason that this script f notation is so common. So we write down omega fp is a probability space if first thing is that p is a measure on the measurable space omega f. Second thing is that the total measure p of omega, the total set has measure 1. Okay, the measure of the total set is 1. One can ask that how am I sure that this omega is also in f? Thing is that I have assumed that empty set is in f, okay, is in that event space. So complement should also be there, since that is the structure of the sigma algebra. So if empty set is there, so the whole omega is also there. Okay, so there is a definition of probability. Now we discuss about what is the definition of Lebesgue measure, because Lebesgue measure would be visited time and again, and this is the measure which we encounter in day-to-day life, like length, area, volume, etc. So we go to the next slide for introducing what is Lebesgue measure. So imagine that you have a real line, one dimension. So here we are just talking about one dimensional, 1D. So assume that you have so we consider first a set of all real numbers. On that we want to introduce one sigma algebra, and on that sigma algebra we are going to introduce the measure which gives length. So measure of an open set, open interval, should be the length of the open interval. I mean that if I have open interval a comma b, then the Lebesgue measure of that interval should be b minus a. Okay, so that is the goal. For that, first we need to define what is the sigma algebra, and it turns out that to define sigma algebra, one has to do a little more work. I mean, this is not very immediate way, there is no particular immediate way to define that particular sigma algebra. Why is it so? Because the main reason is that we can consider taking say sparse set of R, so a set of all subsets. But then one cannot define Lebesgue measure the way we want. What are the properties of the Lebesgue measure? We know that it should be translation invariant. That means if the measure of the interval a comma b is b minus a, does not matter if I translate that interval. So I add 1 million to a and b, so 1 million plus a comma 1 million plus b, that interval should also have the same measure. Okay, so that is the underlying goal. So it is not easy to define such measure. It is not possible to define such measure on set of all subsets of real numbers. Okay, so we need to exclude some subsets of real number, okay, but still construct one sigma algebra on which one can define the Lebesgue measure. Okay, so that construction has many steps. So the first step is that introducing what is called outer measure. Okay, so we first consider this order pair, that RPR, that means R and the power set of R, that is also a measurable space, because the set of all subsets is of course a sigma algebra. Why is it so? Because sigma algebra has two conditions. I mean, those conditions are of course satisfied because it has all subsets. Okay, there is no absence. Okay, however, so on that we are constructing m star. M star is taking a member of power set of R and giving a value 0 to infinity closed, given by mu star of A is equal to infimum of the sum of length of open intervals II, where II are intervals which cover the set A. So given a set A, you consider a countable collection of intervals such that their union covers A. Okay, correct? Union covers A. So given a set A, always you can cover it by some countable union of intervals. It is not a big deal. For example, you can just first take all open intervals of the length of the size length minus n to n. Okay, and then n tends to infinity. Okay, so all possible n. So it would cover, that union of that would be whole R. So that covers all the sets. Okay, so of course this collection is non-empty. The collection of such covered by open intervals is of course non-empty, but we choose any of those and find out this sum. The sum of L of II. What is the L of? So let me write down what do I mean by that. So length of interval A comma B is B minus A. Okay, so that is the straightforward definition that we are going to use here. And here we consider this number, but this number is arbitrary, right? It could be very very bad number. It will be very overestimation of the size of A. Then we consider all possible such cover, and then we take infimum of that, and when we find an infimum, we are going to get some positive real number. Okay, and that we are going to sometimes we may not get real number, it could be plus infinity, and that we associate to be m star of A. Next, we see that this m star, the way it is defined, need not be a measure. However, this has some good properties. It has subadditivity, and m star of empty set is 0. So this m star is not a measure because it is not additive, as I have emphasized here the definition that measure of union of disjoint sets should be sum of the measure of the sets. So that is not true for this m star. So what we do is that we find out collection of subsets of R for which m star has a very good property, and that subset, that class of subsets turns out to be a sigma algebra, and on that if you restrict m star we get the Lebesgue measure. Okay, so let us see, let us consider the set of consider the collection of subsets of R, okay, such that you have the following property: m star of A is equal to m star of A intersection E plus m star of A set minus E, okay, for all A which is subset of R. Okay, what we consider? So here this is a collection of subsets of R. We denote it by script M. So how is this collection defined? It is defined as a collection of E which has a particular property. Which property? That no matter what subset of A you choose, subset of R you choose, the outer measure of A is equal to the outer measure of its two parts. What are the parts? One is the part which is inside E and the part which is outside E. Okay, so the way E cuts A, okay, so in that case, with the part which is inside E and which is outside E, the outer measure of the both, if you add, you are going to get the outer measure of the full set A. Okay, of course, you understand that this is one kind of additivity property. So if you consider such kind of collection and call that M, and it turns out that, so I am not proving it, it needs a rigorous proof that M forms a sigma algebra. Okay. And not only that, if I restrict M star on script M, okay, and then whatever I am going to get, we say that we call that M, okay, is we are going to get a measure because script M sigma algebra, we are restricting this thing on the script M. So then M is a measure on R script M, okay, and furthermore this M has, I mean this needs a proof actually, that I have a sigma algebra and I have restricted M star on script M. What I would get is not only outer measure but that is also a measure. Okay, so this is a result, and then this measure has the following property, that M of any interval A comma B, okay, is equal to B minus A. Okay, so the property what is intended for Lebesgue measure, and also that it is translation invariant. Okay, for this actually when I write down this, I intrinsically assume that this interval is in this sigma algebra. Okay, so that is also one result, that every open set, so every open sets is in M. Okay, so next we go to the question, what is Borel sigma algebra? So here we started with the set of real numbers with power subset of R, which is a very big sigma algebra. There we discussed that we cannot define a measure like length measure which is translation invariant. So for that, and also measure of an unit interval is 1 finite, so that type of measure I cannot define here. So we have removed some sets to obtain a sigma algebra which is smaller than the power set of R. We call this script M is the Lebesgue sigma algebra, and then we restrict the M star outer measure on this sigma algebra to obtain a measure which you call as the Lebesgue measure. And then we are now going to discuss the even smaller sigma algebra than script M. Okay, so as we have seen earlier that this sigma algebra M includes all open sets. Now we say that, okay, what is the smallest? The smallest sigma algebra containing all open sets, all open subsets of R. Okay, so this smallest sigma algebra is smaller than the Lebesgue sigma algebra. We give a name, we denote it by BR, and we call that Borel sigma algebra. So this Borel name comes from a mathematician's name. So Borel was a mathematician. Now we talk about what are the zero measure sets on this. Okay, so before that, let me also clarify one very important difference between these two sigma algebras. Okay, so that is the set of measure 0. Okay, so let us talk about what is null set. So null set, so if A is in script M such that Lebesgue measure of A is 0, then we say A is a null set. Okay, then you say A is a null set, and then every subset of A, okay, is called negligible set. Okay, every subset of A is called negligible set. Okay, now question is that if I have a null set, that means a measure 0, what should be the measure of subset of that? To answer this question, I must have the subset of A that is in the sigma algebra, otherwise I cannot talk about this measure. Okay, so anyway, so if that is there in the sigma algebra, then you can ask this question and the answer should be 0. Why? Because if I cut this whole set A into this, this smaller subset and its complement inside A, then both should have non-negative measure. Okay, and then addition of that should be same as the measure of A, but measure of A is 0. So sum of two non-negative number is 0, that means both are 0. So that actually clarifies that all subset of a zero measure set, if those are measurable, should have measure 0. But the question is, are they measurable? In principle, when we talk about Borel sigma algebra, that often does not include all negligible sets. Okay, so if we consider a particular measure space mu such that all mu negligible sets are in F, then we say omega F mu, this measure space is a complete measure space. Okay, complete measure space. So it turns out that Lebesgue measure space omega and then F is replaced by script M and mu is replaced by M. So that is a complete measure space. So here I write down R M small m is complete. However, R, so M is replaced by the smaller subsigma algebra, that is BR, and M here again on this sigma restricted to the sigma algebra is incomplete. Okay,